team. A few words about me. So I'm a co-founder of Instana. I did most of the architecture and design in there, and I've seen a lot of performance problems in my life. I have a speaker deck where I upload all my slides, and I have a Twitter, so feel free to follow me there. Important, so don't need to take pictures, make notes, whatever, maybe of this slide, because you will find all my slides and the whole presentation on my speaker deck. So, people taking pictures. Cool. So I will today, thank you, Stan, talk about a few things. How we process a lot of data. I will talk about how this data comes in, how we do the processing, how we store a lot of data, and how we present it. We do it mostly on Amazon and mostly with Java, so Java plays a central role in our whole architecture. I will talk a little bit about everything, and I hope there are some useful information in there. I might talk about tracing and monitoring in general, but this is not supposed to be a product pitch for you. It's about backend architecture. There's one little introduction I want to give. So you can watch this on YouTube or now me presenting this. It's a video on the other monitor. And it's pretty long, so let's play and fast forward. I will give you a little introduction on what this is. So you see Instana as a user interface where we visualize all the data we are collecting at any point in time. And there are a lot of boxes on here which represent servers. And we're collecting live data every second, so we are not really aggregating data. There's a continuous stream of data. So what my colleague Michael did here, he is looking at a specific machine where he's going to start a new process, and we are collecting the basic infrastructure metrics, which are quite boring. But what he's doing now, he is starting an Elasticsearch. And that Elasticsearch process, as you can see, it takes up CPU, it takes up memory, and it starts to ramp up. And on the left-hand side, what's happening is that continuously Instana is seeing, oh, there is an Elasticsearch now online. And so you can click on it and actually inspect that Elasticsearch, what it's doing. Well, it was started up freshly, so it's not very interesting right now. But we collected a lot of static data, which makes sense to understand how this Elasticsearch is set up. Now that we are inserting a document, suddenly the data is going to start. Tons of data. It's useful data when you know how Elasticsearch operates. This all is very helpful for you. But Elasticsearch alone is not the really interesting part. There are more interesting parts to it. For example, Elasticsearch is a Java virtual machine which can have garbage collection problems. So you see, data is coming in from various sources just by starting one of what we call agents. And Elasticsearch is not alone. We have 3 Elasticsearch boxes. So what we are having here as well is a cluster view. So we aggregate data from 3 Elasticsearch nodes to a simplified view which visualizes the whole cluster. So it's multiplied and it's analyzed at a different level. And one more thing I want to show before I stop the video, and you can enjoy the rest at home if you like, is that we are not collecting only metrics, but we are also looking at the whole interaction of every service deployed in there. So those are microservices, and they are talking to each other. And you can see the core weights they are having, the latencies they are having. This one obviously has a problem. It's colored, and so you can look at this. So there is a whole bunch of data we visualize and update every second. So let me find my cursor to close this. Here we go, and let's continue my talk about this. And I first want to talk about the edges of the processing pipeline. You have seen here already without realizing. Thank you, Stan. So the edges of our processing pipeline is, first of all, you have seen a user interface. And that user interface is unlike many other web UIs. So it is a web UI. It's written using React and 3.js. And it has a lot of pre-configured views. So we are not a dashboarding tool where you need to decide on how to visualize the data. We do that for you. We have a means to develop those dashboards. It's always updating constantly, and it's real time or near real time. That means when it happens, you see it. This is based on a WebSocket connection powered through SockJS. There are a few things I would like to highlight. Is React has a very nice model for building those applications. When you have a lot of change, you never manually need to update how the new HTML should look like. You just update the data, and React will figure out what's the minimal change that's needed to be done to the application to make it look that way. We stored all the data in Flux, which is a stream-based state model behind that. And we have a few so-called subscriptions using RxJava. I will talk a little bit about what those tweaks are later on the backend part, because the same ones apply here. What we also needed to do is custom charting. It turns out there are tons of charting libraries out there, but none of them likes to get a new data point for 1,000 data points every second. So we needed to do that and take care that there is hardware acceleration going on. So luckily, new notebooks always have graphics cards, which tremendously helps to make this really look nice. And then let's look at the other part. Where's the data all coming from? So we have what most companies like that have, an agent, which is a process that collects all this data. And it collects them using various means. So it might poll data sources, you might push into it, and it monitors really various technologies. This is just a quick excerpt to overwhelm you with, showing, yes, we can monitor everything. But the challenge is we are actually doing that, so this is producing tremendous amounts of data. As said, we are also getting trace data, and everything is running on timers. So when you think about the whole streaming architecture in the backend, when does it start? It starts all when the agents want to emit something to the backend. Without an agent running, nothing would happen. The backend would idle, the UI would idle. So as soon as an agent sends, it's going to happen. Now agents run on timers, like every second sending data. And the agent is really low overhead. Now when we look at the whole backend architecture, now that I have defined my borders, so it looks roughly like that. We have API on the left-hand side, which is fed by agents, and API on the right-hand side, which goes out to user interfaces, other integrations. It really helps to have an API level defined where you then can say, OK, data is always coming in that format, and it's going out in that format. Talking about then the core of the processing pipeline. So you could say, when an agent sends data, just pipe it through. I don't care what's happening. But however, this is not really sufficient for what we want to do at Instana. We want to understand what's going on. So when then Elasticsearch is coming up, we want to know it's part of an Elasticsearch cluster. It's running on a host. When you do your web app and this makes a search request against it, so we want to connect it somehow. So what we are doing is we built a canonical graph of everything. We put it together, all the relationships we have discovered. But how does the data come in, right? So agents are running on a timer. It turns out that it's very helpful that agents are not time synced. So we have what we call an acceptor component, and it gets all this data in. But what it does authorization, so it checks whether you're allowed to do that or not. It does all the decompression that's happening. It's running on a very new version of Jetty using HTTP2, which is great because you no longer have connection handshakes as with previous web protocols. So you once establish a connection, and then it's good to send on. So I said it's not time synced, and it's good. So let's look into this, why it's good that it's not time synced. This is the continuous traffic that's going on to our system. So what you're seeing is that it's really helpful. It's evenly spread out. There is no brute force syncing on us, like at the beginning of the minute the data is sent. Because it naturally spreads out, and we just take the random spread that is in the data to avoid overloading our system, so that this happily continuously serves at 3 megabytes per second. And once we got this data, we put it onto Kafka. Kafka is a really powerful technology. It's very simple design. It works like a message bus pipe, so you can put stuff on it, and then it's in Kafka, and then you have consumers reading the data. And we have quite a few consumers I'm going to talk about. What's interesting, however, is that we were hitting a limit in Kafka. Actually, not a limit in Kafka, but a limit on the box. So what you can see here on the left-hand side, we were transmitting at about 100 megabytes per second in the peaks. And this was the maximum what our Amazon C4 at 2x large instance was allowing. So we were thinking about what can you do about this. And with Kafka, you have the option to say, just compress the traffic using LZ4, and you just turn it on. It's just a config setting. And you see we're trading CPU, so the load went up. It almost doubled even, so from 20% it went to 40% CPU usage, which is still fine because there's plenty of room. But you can see only about a 10x reduction in traffic. So this helped us to get through. So if you are running a Kafka setup, I can recommend to look at the compression options. Yes, so this is also Kafka. Now the question is, we have many customers. How are we scaling that? Are we having one big magical backend for everybody? No, we don't have that. We scale using a mechanism we call tenant units. It's basically a variation of logical sharding. So we decide up front, half of the data is for that customer, the other half of the data is for that customer. Both get an individual instance. There is an alternative title to this talk saying we use not so microservices. Well, we decided it's better to have larger groupings of our logical services on a single box dedicated for a customer. Customers, of course, don't know this. They have single sign-on, and they don't know where it's located. And we can easily scale using this mechanism. So in this tenant unit, we have two main components, which I call the heart and the brain. So one of them is responsible for all the internal routing and making sure everything is on the same cycle, while the other one is then taking care of understanding what's going on. This is where Stan really lives in our brain. So we always need to make sure we synchronize this data somehow, because it's non-synchronized in the beginning. And that's the responsibility of our first component I here titled Heart of Processing. Internally, it has a much more boring name, which I spare you. It holds the complete state in memory. So whatever you have seen on the map is in memory in that component. It has a complete continuous understanding of what components are running, how many CPUs are on that server, how many servers are on there, are those servers in the same zone, what Elasticsearch cluster is set up, and so on. And whenever data is coming, it incorporates it in that global state. So there's a continuously updated understanding of how the customer's environment look like. And just using the deltas to apply to it is really helpful. So you don't need to rebuild the whole understanding every time something comes in. You just keep it rolling updated. But because the agents were sending just whenever they like to, we really need to understand what is the current time. So what starts here is our canonical time ticking. So this component emits a signal like your heartbeat saying, at this moment in time, this is time 0, whatever. We know how those components talk to each other. What is the technology behind that? That's very easy. It's a big Java 8 process. It has a lot of memory. And it's using Project Reactor, which is a reactive streams framework, which is really nice to use. And it has a lot of nice concepts. So what you can do with Project Reactor is you say, there's data coming in from Kafka. Whenever data comes in from Kafka, do this, do that. And maybe after you've done that, emit it again, and somebody else can consume it. And the programming model is really easy, and I can highly recommend if you have like event-based processing you want to do, maybe you want to do decoupling and scaling with that, have a look at Project Reactor. It helps. We are doing a lot of stuff as listed here, like indexing, but it doesn't really matter. The point is there are various activities that are decoupled and should not really block each other, which leads me to a very interesting point about what Instanas' take is on reactive streams. I mentioned before we are using RxJS with our own spin. Well, the default behavior, strangely enough, in reactive streams is that whenever you encounter an error, you stop your subscription, which makes sense in certain use cases, but I believe that in most use cases you want to continue processing after the error. What you need with the default behavior is like external supervision. Somebody needs to know that your processing now has stopped because it was encountering an error. We have done it the other way around. We have wrapped it with error handling. So each processing step has its own error handling and it never really crashes. That's especially important when you don't control the data that's come in. It looks like we might control it, but actually we are sending data that is generated on customer machines, so it can contain anything and might crash our processing. The second thing people like to talk about with reactive streams is back pressure. Back pressure generally means, I said Kafka sends data, I consume it, I send it out, and then a second party consumes this data and processes it further. It means that you have means of saying that the second party is overloaded. It says, stop, please don't emit new data, and then this prevents all the previous steps from happening, which is a nice concept, and it allows flow control in that system. However, it turns out that most of the time you can't really stop your producers. We can't tell our customers to shut off the agents. They should produce new data, and they should continuously process data. So we are never going to back pressure to the end. However, we use, of course, back pressure mechanisms to make sure that individual parts of the pipeline know what to do. And what I think is very important when you do this type of reactive streams architecture, at every stream you should apply some metrics, figuring out, are you actually dropping at that step? And then I have an example here where we were alerted that we were dropping. So this is a processing step inside Instana, which processes traces to the application map. And because of load increasing on the system and the failure in our Cassandra, in Elasticsearch, this was backing up. And this created a problem. When you wouldn't have added a meter to it, you would have no way to find out that this reactive stream internally is dropping, which might be a problem. You might accept certain drop rates, but not drop rates like this. I mentioned Cassandra, so we are writing to Cassandra. And there's an interesting tidbit of configuration I want to point you at. In Cassandra, you can configure whenever you insert data how long it will live. And it makes sense for any kind of big data processing that at certain time you say, I don't really need that data anymore. So you will always have a time to live, TTL, or expire set. In our case, it's like we are building roll-ups. We are making second-level metrics, 5 seconds, 10 seconds, minute-level metrics. And when you go back a year, you don't have access to the 5 seconds anymore. But we were writing them all in the same table space. And then Cassandra was going and saying, OK, this data is dead. It's no longer used. It puts a so-called tombstone on it. And then it might delete it later. But it's never deleting it because the table was so fragmented. So what I would recommend is when you are having data that has varying lifetime, make sure that you put them into separate tables so that you can treat the table at once. And what we also did is we put it to a date tier expiration policy in Cassandra, which tells you that the age of it should really determine when it's deleted, rather than some TTLs. We have Elasticsearch, and what I want to point out with Elasticsearch is we have one Elasticsearch cluster for all the static configuration data you see, and for events. This currently has 840 million documents indexed. But we have a separate cluster set up for our tracing use cases, which is a way more frequent write use case and actually very seldom read use case. This currently has 7 billion documents indexed here. And it writes with about 8,000 writes per second. What Elasticsearch does is you can assign various indices to Elasticsearch, so you have a different schema for your data. But what you can't really separate is the thread pools Elasticsearch internally uses to update the data, expire the data, update internal indices, update Lucene, and so on. And because the access pattern to those type of data is so different, these threads were constantly not doing exactly what we would like to have them to do. So what I can recommend is when you have a really different access pattern in one part of the application and another access pattern in the other part of the application, separate it out. It really helps the database, whatever it is, in this case it's Elasticsearch, but it applies to many databases. It helps to optimize for the one use case. Even when you don't tell the database exactly what the use case is, it will figure it out. So we have set up 2 clusters at the moment. We use Redis, so we are storing a lot of data to Cassandra, and it has an insane amount of writes. But we are showing in the user interface also data when you open it for the last 10 minutes, which is every second a data point. This is way too much data to write to Cassandra, and actually we don't really need it to be stored. So we decided on putting it into Redis, into an in-memory database. We turned journaling off, which means that Redis will never try to persist it. And we had problems with TTLing. So the same thing I described for Elasticsearch, making sure Redis deletes in the background the old data you don't need anymore. Redis couldn't really keep up with that. So the way we dealt in Redis with that is we came up with our own algorithm to name the keys we are writing to. So we are self-overwriting the data we have previously written to Redis, and we don't need to issue an expire command to Redis for that. So this is a trick you might want to look into all your data stores and how they handle expiration. Really carefully check it. Maybe you can help it, or in this case, do it completely on your own. Maybe a completely different mechanism. So now that we have always the state of all components that we monitor, and we have this persistent to the data stores, we actually want to do actions on it. And one of the key actions Instana does for you is figuring out whether everything is still okay. So you might have seen that boxes were red for various reasons, and we want to figure that out. So we look at all the data coming in, and we find out what are problems that we can deduce from that data. We build time windows containing historic data, and we are analyzing for trends. We are having a neural network we are feeding to figure out are there certain normal behaviors over time that may be violated. And this is also done all in one component. It forwards out the problems it finds over Kafka again. So this is really the analyzing part. And what we use as one of our key algorithms in the whole processing is using the median absolute deviation. It's a little bit like the average you have in your data, but it's way more robust against noise in your data. And especially time series data, you are updating every second all the time, is noisy. You can try to smoothen it, but I would rather not do it. It's unnecessary overhead. Just use a mechanism which is a little bit more robust. And the median absolute deviations are that. And we use a neural network. We initially started with Google machine learning engine and TensorFlow on that. But we have an on-premise deployment as well, so we don't want to really only use it. So we have an own installation of a neural network that we are training. So algorithms we are using like this. It's an outlier detection. So you see that this data here is very noisy, but it has distinct variations in its shape. And you might see the dots above the line, this is where we detected outliers. Surprisingly, this one spike, it didn't qualify as an outlier because it was not reliable enough for the algorithm to detect. It needs a few more data points. You can consider this good or bad, depends on how you look at it. And the algorithm we use here is the e-devices with medians. It's the Twitter paper, because Twitter made it popular to detect trends in data. We also have trend detection built in. What I would like to point out with trend detection is no matter what trend detection algorithms you are using, you will have a smoothing problem. So you see those boxes are not continuous. For example, this box in front, the blue data clearly shows a trend, but the boxes, the trend detection algorithm is not 100% with that. You could try to make it so that the algorithm can figure those out, but it turns out to be way more efficient just to accept this and then do a second pass on it and do a smoothing of the results and figure out, oh, between the boxes there is just a gap of 1 or 2 data points, so we ignore that one. Then we have an outlier detection algorithm, which is basically the same as the sudden change detection we have here. And then we also have predictive algorithms, which are really cool. So with prediction, you have various things you want to see. For example, that at the lower bottom of the green line, you have a stable curve. At the upper one, so this is clearly like a day rhythm, you have more fluctuation, and you can see that there is a general trend of this whole curve. And at the blue line, we do our prediction. And what's marked in gray is our corridor, where we predict the data to be in. And when it's not in the corridor, it's treated as an abnormal value. So this is how it will look in our product very soon. So you see there are sections marked in red. This is training data from a customer. So at that point in time, it was an abnormal behavior. It's not yet saying it was bad. It's just one more data point we now figured out. And we can predict stuff like you will run out of capacity tomorrow using this algorithm. Yes, so as I mentioned, those are not so microservices. They are all communicating via Kafka. But when we have like our heart and our brain, they have a lot of responsibility. Internally, they are, of course, modular, but they act as one Java virtual machine. The reason for that is, well, copying such large amounts of data across the network to another microservices does not really help you much. In fact, we have so much data that's continuously updated. We have a lot of shared state that syncing it over network would be impossible. So we have a plugin architecture within those not so microservices, but we avoid the copying. I have a more extreme optimization example here. Is so when we read data from Kafka and we want to convert it in our data model, and this data model is then passed on and converted again, I have two options here. Option one is we read from Kafka and then we decompress this, and then the bytes we have decompressed pass on to a second thread, which then takes the bytes and makes a domain model out of it, passes it on, and then a third thread does the processing. And then there is option B, which reads from Kafka, decompresses, builds a domain model, passes that on, and the second thread does the processing. Quick poll, who would do it the way option one would lay it out? Okay, somebody option B? Okay, or a third option, I see. So from a software designer perspective, option A is a little bit more attractive because it's decoupled, it's isolated, and one thread is only doing one thing. But it turns out that when you run this on a JVM, there are optimization techniques that favor option B, actually. So for example, thread local allocation buffers means that data that is handled within a thread has a chance to vanish So it's not affecting the way heap is handled, because the JIT can figure out, oh, this data is just used temporarily here, so I don't need to make it available to anybody else, less synchronization. So this tiny thing is basically showing the same. Passing data around when you have a lot of data can be expensive, so really think about what to pass around. What we also use in Java is we are using G1GC, which is the new garbage collector that finally became default in Java 9. It's really good when you have a lot of data modification in your heap and you can have large heaps. So we have components that run with 20, 30, 50 gigabytes of heap, and G1GC makes it really nicely. When you don't really control your data like we do, so there's a lot of strings coming in on primitives types, which I would recommend to use a dedicated library for to reduce the memory overhead. String deduplication is a very nice feature of G1. So when a string comes in and it's held in memory, and later another string comes in and is held in memory, and those strings are identical, G1 will, in a separate path of the garbage collection, look at all the strings and figure out, hey, you have 2, 20, 100, a million identical strings in memory. Let's throw them all away except one and use that reference. So it's really efficient. It cuts like 99% of our strings we are processing. It just deletes. So it's really nice. And then you get like models like this. This one has 12 gigabytes of memory, and you see it's happily working very steadily. I want to talk a little bit about how we update and deliver. So our agents are updated continuously all the time. Updates are downloaded dynamically by the agents. Our backend is released like bi-weekly, roughly. We release it first on our SaaS platform, and should there be no problems, sometimes there is, like we do a hotfix the next day. After a week, we release it to our on-premise customer, where we have less access to. And this is all operated on Amazon. I want to share a little bit how we manage those components. So we are using the HashiCorp stack, which is not so well known, I figured out, but I think it's pretty neat if you want to have a look at how to do config management, on how to provision machines, how to exchange status. Nowadays, everybody does it with Kubernetes, but with HashiCorp Nomad, for example, we schedule our jar files on bare metal without the need of Docker containers. We have it all in VPCs and various availability zones for high availability, and we have quite beefy boxes. This one has 120 gigabyte, which is really nice. With Amazon, you can get large hardware very easily. One tip I have is when you build up multiple components, even though you have service discovery mechanisms, like in Kubernetes you have, or here we're using Consul to do service discovery, while it can deal with complex service change and maybe even cycles, it makes life much more easier if you have a well-defined dependency chain, like this set of services always needs this set of services, so you can start this up first and then that. And in the recovery, it will fix this. Scaling on Amazon is also very awesome because you can do it. It's super straightforward to do. But the problem is it's not really flexible. And I heard that on Google you have way more options to customize your machines. In Amazon, it's quite often it's double or nothing. So you can, for example, scale IOPS, and we needed to do that for our Cassandra instances. They have a very high I/O operations per second requirement. And you do that by buying more disk space. So even when you don't need it, you have like terabytes of disk space available, and that's depicted in the lower left-hand graph, just to ramp up your I/O operations. And so we have a lot of empty space because we bumped up disks, I/O ops buying disk space. And same applies to machine size. I have shown you that once we had our Kafka at capacity limit at the Amazon box with 100 megabytes per second, Well, it also scales quite linear. So you double the cost of the machine, you get double the size, double the bandwidth, but not always need to do that. So once we applied the compression, we now have way more breathing room. But that's the option to scale. And an often overlooked fact about Amazon is that inter-availability zone traffic costs money. It's very little, like a cent per gigabyte. But when you have a huge cluster set up, the cluster does continuous replication amongst its nodes and gossips the state. This can actually sum up to a significant amount of money. I'm not saying don't do it, you just should be aware that you're not having any surprises when you deploy on Amazon, because you definitely should be doing it in multiple availability zones should one fail for availability, of course. And one thing I wanted to mention, so everything I've shown to you, you have seen screenshots. We use us to monitor ourselves, so we drink our own champagne. Don't worry, boxes are red. This is stuff that's continuously fixed. And it's important that it's continuously monitored, because stuff can just turn red and you want to know why. And I hope to have given you some insight on how we do that, how you could process large amounts of data, what are the important things you might want to watch out for. And last thing I wanted to mention is that I'm hiring. We have an office in Novi Sad, and we are looking for people helping us to build more of our processing engine, maybe the algorithms. Maybe you're interested in operating this huge mess of components. So I really would like to talk to you if you're interested. So thank you very much for your attention. I might have 2 minutes left for questions. So is there any? You have a microphone there?
Yeah. So we have a microphone, and I know the bot is crying for attention. I don't see any questions here, so yeah, please do so. But yeah, let's use the mic.
So it was a very interesting presentation, and I have one only question. How you manage the mistakes or bugs when you deploy something and something was wrong and your messaging produce wrong data, and how you manage it in next stages? How you?
Yes, so there are two sources where stuff can go wrong mostly. One is the agent side, so agents are sending data that is broken. We have a continuously updating agent, so once we notice that in the backend, we have, as you have seen, our own alerting on error rates throughout the system. We just roll out a patch for that. For the backend, I mentioned, yeah, stuff can go wrong. This is why we have a guard time for our on-premise deployment, where we don't have access to this information, which is what I like about SaaS as a provider. SaaS is so much more valuable to you because you get all the errors that might be silently occurring in the system. So we monitor that continuously, and we can roll back, of course. And we can also quickly fix, and this is what we do most of the time. So after the release, we get like performance improvements or stuff that's not 100% working. So we roll out a fix on the next day, basically. It's just normal procedure. We put it into Nomad, say deploy to those customers, and after a minute, it's deployed. So it's quite nice.
What about already produced data? What about data you already produced wrong?
Yeah, so we of course have one advantage compared to other use cases. So I mentioned we might be dropping data. We might be producing wrong data. This is not really life-threatening when it happens. And we are not going to correct this data. It's happened in the past. It might show up as a spike on a dashboard, but this is just fact. And customers accept this when you explain it to them, how there was a faulty version. Or it can also happen that like the new version of Elasticsearch suddenly changes the granularity of a metric from milliseconds to nanoseconds, and suddenly the value is way higher in our dashboard because we didn't know it was happening. So of course this happens a lot when you have such a wide coverage of technologies you're supporting. but we just move on with that. And it's not so critical if it happens. It's not so critical when we lose a minute of data. But that's our use case. Your use case might not allow you with that. So I consider myself lucky in that regard. Yeah. If there are more questions, come to me later. I guess that's it. Thank you very much.
You can wave at the audience at the live stream.
Thank you for watching at home. If you like this, please rate. This is what I need to say, right?
Yeah, rate.